What does that mean? D on FRQ check. Like you had trouble with the FRQ check? The progress check? Did you find that one to be challenging? We can definitely look at the classroom progress check as well. And we can definitely look at that. Yeah. Yeah, sure, that's fine. That's why I'm recording it too. I mean, I don't know how long it's going to take, but probably longer than 4 o'clock. So I am recording it, and definitely we can take a look at the progress check. All right, so let me go ahead and log in there. I'm going to go ahead. All right, go ahead with your question. Was it on this question, the KSP question, or was it on the second question? Question 2, okay. So here, looking at this question, you know which part it is? Part D, okay. Does the value of Kc increase, decrease, remain the same when the temperature is decreased? Justify your answer based on the expression for Kc and the concentrations of products and reactants. Okay, so, oh, you meant E. Okay, the particles one. Is that correct? And the empty box. Draw an appropriate number of each type to represent the possible new equilibrium at the lower temperature. Okay, well, let's see here. We need to know the so at the well, first of all, before we can decide that, we need to focus on up here. They gave us the reaction. They gave us the delta H. What does that delta H tell you about this reaction? It's exothermic. So where is the heat located, or where's the energy located? On the reactant side or the products side? It's on the products. Okay. So temperature is decreased then. Temperature is decreased. That means you're removing heat. So you're removing from the product side. Which way does it shift? Does it shift towards the reactants or towards the products? So it's going to shift towards the products, right? And when we do that, when we shift towards the products, here, let me pull up a blank one so I can show you basically what's going on here. Draw. So we're shifting towards the products, and let me look back at the reaction real quick. So it is H2 plus I2. So we have H2 plus I2, so 2HI. And we're shifting right towards the products because the temperature was decreased. And we also know that heat is a product over here, like so. So that means, let me just do that. All right, so temperature's decreased. Heat's a product. So remember, the general equation is products over reactants, although technically for this one, the Kc would be HI squared over the concentration of H2 and I2, like so. So if it's shifting to the right, we're making more products. That means we're making the numerator here bigger. This number is going to get bigger. So then Kc, well, that's terrible, pencil. Oh, hold on, let me add a pen. And we will make that blue. So Kc, therefore, is going to increase because we're increasing the numerator. We're shifting to the right, and actually, we're consuming some of our reactants. So the reactants are decreasing, the products are increasing. That also means that the forward reaction should speed up a little bit. It's going to, what is that? Why does it keep doing that? The forward reaction is going to speed up because the temperature is decreasing, so if the forward reaction is speeding up, that means the reverse is going to be slightly lower. Actually, technically, no, both reactions are slowing down, except for because we're decreasing temperature. When you decrease temperature, you're lowering the kinetic energy of all the particles, so you're actually technically slowing them down. However, the forward reaction is going to be faster than the reverse reaction. So let me keep that up. That's why this ratio of products to reactants is now going to change, because we're actually changing the rates of the forward and the reverse reaction. So basically that's what's going on here. And so you should have, in your drawing, you should have more HI. Now, I don't know if there's like a technical amount that you're supposed to have in there. Draw an appropriate number of each type possible new equilibrium at the lower temperature. Did you actually calculate the new equilibrium at the lower temperature or no? Anywhere on here? So this is saying the original value of the quotient was, okay, so that one you're just deciding which way it's going to shift. On the graph, 3 curves. Draw those. Kc is 49. So here you have 1, 2, 3, 4, 5, 6, 7, 8. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10, right? So that means we have 1, 2, 3, 4. So I would say you would have like this one. If you're drawing this one over here, because we have to show that it has more product now. So what is our box going to look like here? Our box should have the 10 HIs in here. Okay, you should have those already there because those were already in the box to begin with. I believe you had 2 of these like this, right? So what I would do then, if I'm drawing this to show that more HI, because Kc increased, we have more products than we do reactants, I would make one of these react. And if we did that, we made one of those react. In the second box over here, we would still have our 10 HIs, you know, draw those like this or whatever. But then one of these reacts, so then you're going to have 2 more of those because, you know, each one creates an HI because there's 2 I's and 2 H's. And then you should just have one left of the other. Because remember, at equilibrium, you're going to have a certain amount. I mean, it's not, we're establishing, yes, the Kc is going to go up and it's going to shift more to the right and make more products in terms of the K value of the proportion of the products over reactants. But there is still going to be some reactant in there. You wouldn't just completely take out all of the reactants because that would be assuming it goes to completion. And here we still have an equilibrium position to maintain. Does that make sense? So I draw this and then you would include 2 more of the HI here, and then you would leave the last 2 reactants behind. Now we would have to make 2 because if we react the H2 with the HI, if those are going to react, it is actually going to result in 2 of the HI over here. And you can't just half react one of, you know, half of the reactant. You have to completely react the reactants. And that's what we would get. All right. Any more questions on this FRQ right now before I move back to the checklist and other things? Does anybody have any more questions on this? I do want to point out 1B. Yes, that's one I actually wanted to talk about. Okay, so 1B, so here you have a KSP problem because we're dissolving lead 2 iodide, and it has a very small KSP, so not very much of it's going to dissolve. And this is the dissolution of the lead 2 iodide going on. And here you would write the KSP. That's great. And what you notice, if lead 2 iodide is dissolved in 1 molar sodium iodide, is the maximum possible concentration of lead in the solution greater than, less than, or equal to the concentration of the PB solution, part A. Now, I don't really like their explanation here or their scoring guidelines. This is the one I was talking about in class 2, because I don't really like their scoring guidelines because they don't really refer to the common ion effect. But remember, you can think of this as a Le Chatelier problem, because if we have PbI2 dissolving, you're going to get the lead and then the 2 iodides. But if we're putting it in 1 molar NaI, well, this is a soluble salt. Okay, that's a soluble salt. So what's going to happen here is that's going to break apart into Ni and I minus. So technically, what are we adding in? We're adding in iodide here. And if we add in a product, which way does it shift? It shifts left towards the reactant. And the reactant happens to be the solid. So it's going to pull some of the lead 2 ion out of solution. So it's going to make it less soluble. So it should, the concentration of the PbI2 is therefore going to be less. And that's not really, the way they explain it, I don't like it because it's really due to adding a common ion. It's called the common ion effect. We added the I, or we added it to a solution with a common ion. So that means less of the lead 2 iodide will dissolve. Because there's already this amount present, and it's only going to hold a certain maximum of each of these ions in solution. And since some of this is already present, that means less of your salt is going to dissolve. But it is because of the common ion effect, because the iodide is already in the solution, the sodium iodide solution. And adding a salt to a solution with a common ion always decreases solubility because of Le Chatelier's principle. Adding it here makes it shifts that way, so you get less of the dissolved ions and more of the solid. That means it's less soluble and there's less concentration of each ion in there. Well, the only one that would decrease here is the one that's insoluble, that barely dissolves, because sodium iodide is already broken apart. This one completely dissolved. It's not even an equilibrium position, because this one pretty much just completely dissolves. You have sodium ion and you have the iodide ion. Remember, anything with an alkaline metal is completely soluble. So this one doesn't even really have an equilibrium position. It just goes this way to completion and completely dissolves. The ones that have the equilibrium positions are going to be the ones that have like smaller KSPs, that have a small ability to dissolve. Okay, so that's a good question. There is going to be one problem that's about KSP, and there's like one to two problems, depending on if you get one of them's really like a longer one, and then the other one I've broken up into two, like it's two smaller equilibrium questions. This is just going to be on equilibrium, like regular equilibrium, not KSP. I was counting it up. That's a good question in terms of time. So counting it up, there are about, about 12 parts. So it's going to be about 30 minutes. So right now I'm going with 30 minutes for it to close, and then maybe 5 minutes, you know, for the upload kind of process. But 30 minutes is kind of what I'm gauging for here for the quiz. Anything else about this FRQ? The progress check FRQ before I move back to the checklist and other stuff. Okay. All right, so then let's look at the checklist. And I'm going to kind of go, the top part of the checklist is mostly about KSP. So we're going to start with KSP. Everybody's getting a KSP problem. You know, be able to write the dissolution. And that's the one like this, where you're doing like the PbI2 and you dissolve it into Pb2 plus AQ, and then the plus, sorry, I'm not doing a very good job of doing that. Hold on. Where is my eraser? I can't find my eraser. Is that an eraser? No, that's not an eraser. It's not letting me. Oh, well, here, let me just do that. I'll start over. So like PbI2 dissolving and getting Pb like this, and then the 2I minus, and then these would be AQs and whatever. So that's dissolution. Be able to write out one of those reactions. Water interacting with the cations and anions in solution. I hope you could draw that by now, because if you have the lead, which way are the waters going to face around the lead 2 ion here? Which one faces in, the oxygen or the hydrogens when they surround this? It should be the oxygen sides that surround, yes. So, you know, you would draw it like this, with facing that way. And then if you had the iodide, you would draw the hydrogens facing inward, because those are partially positive. So yeah, you want to make sure you can do that. Understand the measurement solubility. Does everybody truly understand what we mean by solubility? Solubility reference is molar solubility. That's one way to do it. And how do we measure molar solubility? I don't know if I spelled that right, but whatever. What is the measurement of molar solubility? Yes, molarity. So that's just moles over liters. However, is every measurement of solubility in moles per liter? No. They could give you like grams per milliliter or something like that, right? So you generally, you know, if they are going to give you some kind of problem where they give you the, they could give it to you in grams per milliliter and expect you to do a conversion before you start. So always expect that. Like, they don't always have to give you moles and liters. They can give you other stuff, and you have to convert it first. So grams is molar mass, you know, milliliters, 1,000 milliliters equals 1 liter. So that's one possibility. Molar solubility is how much can dissolve at that particular temperature according to that equilibrium solubility product. No, for KSP, the molar solubility is usually calculated from the KSP equation. So that's what we're going to look at there. Solubility is the equilibrium of the salt in water. So that's the amount maximum of the salt that's going to dissolve into its ion in that particular amount of water. Now, solubility curve, you know, those are in your notes, where it's usually a certain grams of the stuff out of the grams in 100 grams of water. But as you see, the other thing on the solubility curve is temperatures, and a lot of them are affected by temperatures. So increasing the temperature makes most salts, not all, most salts dissolve more, because most salts have an endothermic dissolving process where if you increase the temperature, more of it will dissolve. Not all salts, but a lot of them on our solubility curve shows an increasing trend, which means as the temperature goes up, more will dissolve. There are some salts, though, on the solubility curve that go like this, where they are exothermic, and they will actually become less soluble as you increase the temperature. They are more soluble when it is a lower temperature. We're going to compare solubilities of different salts with their KSPs or their molar solubilities. Now, remember, the only time you can directly compare the solubilities of different salts by their KSP values is if they have the same ratio. You cannot compare them unless they have the same ratio of ions. If they do not have the same ratio of ions, you need to calculate the molar solubilities of each and then compare the molar solubilities. How do you calculate the molar solubilities? You follow this, like if it's, this is the 1:1, right? This is the 1:2, this is the 1:3, and this is the 2:3. For the different ratios, solve for x. X is your molar solubility. I can calculate the mass of the salt given volume, saturated solution, given the KSP or the molar solubility. Yes, so those are all just conversion things you can do after the fact. I can calculate equilibrium concentrations given KSP or molar solubility. Definitely can show you that too. I can use the M1V1 to determine concentrations after they've been mixed. Remember, that's the QSP versus the KSP type problem. And we also just talked about the common ion effect, where anytime it's in a common ion, it's going to decrease the solubility. And it's going to shift left towards the salt, the solid salt. All right, we're going to cover like pH again. Don't worry about pH so much because we're going to cover that when we hit acids and bases, lowering the pH, and that, you know, decreases. The complex ion formation, remember, generally goes in the forward direction, so it usually increases the solubility of the salt. And we already talked about the common ion effect. So the negligible part, yes, removing that, and then the presence of the common ion in the Rice table. So this pretty much covers everything about KSP. So let's look at KSP problems specifically and talk about these examples here. So writing out the expression, that's always a given, having to write out the expression. So what you want to do here, you know, never include solids or liquids in any of your expressions. KSP is only going to have the two products, which are the ions, because they're AQ and they have a concentration. So concentration of the magnesium ion and then the fluoride ion squared. Now, if we read this in a saturated solution at 18 degrees, it's the concentration of the magnesium is 1.21 times 10 to the minus 3 molar. So it's already telling me at 18 degrees, this is the value right here for this one. That is the concentration that would go in there. And now it wants me to calculate KSP. Well, how do I figure out how to calculate KSP? Well, if I know the concentration of magnesium, I also know the concentration of the fluorine. It's just double the magnesium, because every time this splits apart, you get one magnesium and two fluorides. So you would just, all you have to do is make sure, remember this is X and this would be 2X. So you would do the 1.21 times 10 to the minus 3 here, and you would double this concentration. So this is the doubled concentration, and then you would raise it to that power, and that's going to give you your KSP value. All right, and we do need that for the next part. Hold on, I just need to get out of graphing for some reason. It went to graphing. I quit. There we go. All right, so 1.21 to the times the 0.00242 squared. All right, so I'm getting for my my KSP, because we're gonna need that for the next one, is 7.09 times 10 to the minus 9. So if they give you a concentration of either one of these, you should be able to figure out the concentration of the other. That's no problem. B though, and there's only a couple types of KSP problems. we see KF either adding or not adding to the solution or whatever. We're magnesium fluoride. So this is a common ion effect problem. So you're going to see common ion effect problems. What do you do for common ion effect problems? What do you need to create? What do we create for the common ion ones? You should always create a rice table. Yes. Here is your salt, like so. Create the rice table. So RICE. Now, the solid doesn't matter. We cross that one off. However, initially, okay, we have this saturated, but we're adding this to it, okay? So this is 0.1 per liter is being added. And if of the KF, it's actually the F that's being added. That's this part that's being added. So this is where I put it in. I'd put it in right here, 0.1, this 0. So then this would be plus X plus 2X. So 0.1 plus 2X and then X here. Now, since we already know our KSP up here, we can now solve, times 10 to the minus 9 is going to be X times 0.1 plus 2X squared, right? Now you can graph this. You can put this in as Y1 or you can put this in as Y2. But we're going to assume X is really small and we're going to cancel it out and we're going to eliminate X. Okay. We eliminate the X there. This should work. That's going to be like 0.1 squared, 7.09 to the negative 9 divided by the 0.01. So what am I getting for X here? Oh, wrong pen. For X, I'm getting 7.09 times 10 to the minus 7, right? Molar. Did you get that? Is that what we got? I think that's what we got. Oops. You always, okay, so yeah, that's a good question. I like that question. So you're asking out of these two factors, which one do we remove? Because we're multiplying this times this squared. This is such a big number in comparison to anything that X is going to be. This 0.1 is way larger. So where you eliminate X from is always the one that has the common ion. So that number is way bigger than anything that you would add to it. So even if I multiplied this by 2 and added it to 0.1, would it actually add in? No, it would be like discarded because it's not even close to reaching sig fig rules there. Because 7.09 times 10 to the minus 7 is a really small number. So is that really going to affect anything? Not really. So you're going to see possibly a common ion effect type problem like this where you set up the race table. That's going to be one of the deals that you could see here in the KSP problem, because there's like 3 versions of the KSP problem and you're pretty much guaranteed that each class is getting a different version of the KSP problem. So this is one that has common ion in here. The next one is C here. This is a good example on C here because this one is like the QSP, KSP type problem where you need the M1V1 equals the M2V2 type deal, right? Does everybody remember that type of problem where you're taking like the 2 separate solutions in the 2 separate beakers and then you're adding them together into one beaker and you're trying to see if that's going to precipitate or not. Do we remember this problem from the notes? Yes, no? Okay. Well, I definitely go back to that one or look at this one. Definitely, you know, you could look at this one in the, but you're taking, okay, so because we're still, this whole problem is really focused on this magnesium fluoride dissolution. So predict whether a precipitate of magnesium fluoride will form when you have 100 milliliters of the 3 molar of magnesium nitrate, which nitrates are always soluble. So we know that this one, if this is the magnesium, and this one has the nitrates in here, this is all dissolved floating around in here. Sodium fluoride, we also know, both of these are soluble because alkali metal stuff is always soluble. But when we combine these two, now the magnesium and the fluoride are going to be added together in this new beaker. And I guess I should make it a little bit bigger because we're going to get a new volume here. Because remember, we have the 100 milliliters and the 200 milliliters. So the new volume is going to be 300 milliliters here. When we dump them together, though, that's going to make their concentrations change. So that's why you need the M1V1. So if I was looking at the magnesium part here, magnesium, I don't really care about the nitrate. The nitrate's not going to react. It's going to stay soluble. But if I'm looking at the magnesium, its original molarity was 3 times 10 to the minus third. Its original volume was 100. But we're going to get a new molarity when we combine it because now we have it out of 300 milliliters, like so. So the new molarity, oops, -3 times 100 divided by 300. So this is actually the new molarity of this 0.00100 for the mg. Now we also need to do the one for the fluoride here. That's important. So that's the 2 times 10, here's fluoride, to the -3. That's its original molarity. And it was originally at 200 milliliters. And of course, now its new molarity, once it combines, is going to be 300. So 2 to the -3 times 200 divided by 300. This gives me my new molarity, which is 0.00133. So this is the fluoride. Now we want to know, these would be considered like the initial concentrations before, so that's why these would be used to find QSP. So here we go, we're going to find QSP, and I'm going to do that in green here. So QSP, which is the same expression as KSP, is going to be the concentration of the magnesium, 0.00100, times the concentration of the fluoride, 0.00133, but this is squared. If you go back up, you remember it's, you know, broken apart with 2 of them. So we calculate our Q, and then we compare that to the KSP. So for QSP, I'm getting 1.77 times 10 to the -9. Now my KSP is 7.09 times 10 to the -9. Which value is larger? So we have KSP versus QSP. Which value is larger? 7 times 10 to the -9 or 177 times 10 to the -9? The KSP is larger, good. So it's going to go this way. So does a precipitate form here? Will we have a precipitate? No, we're not. No precipitate. Why? It's pointing the direction. It's going this way, dissolving. It can dissolve more. So, you know, MgF2, you know, this direction, Mg2 plus 2 of the F minus. It's going this direction, so it still can dissolve more. If it was the other way, if KSP was less than QSP, then a precipitate would form. So this is no precipitate here. And yeah, it's a lot of work for this problem because you got to, figure out the initial concentrations, and then you have to dump them together and then find the QSP. So common ion effect, QSP, KSP problem. That's another thing. Those are the other ones that you could see here. Now for D is more of a like Le Chatelier one. It says at 27 degrees, okay, where the temperature has been increased, because the temperature was, what was the temperature? The temperature used to be what? 18, right? So we're definitely increasing the temperature here. And it's saying that the molar solubility is 1.7 or 1.17 times 10 to the minus 3 molar. Well, what was the original molar solubility? Well, we didn't actually figure it out, but up here, the molar solubility is going to be the same concentration as magnesium, right? Because it's 1 to 2 here. So basically the 4x to the third here, you could calculate it that way, or you can refer to the formula unit, which represents the molar solubility, is equivalent to the mole ratio of the magnesium. So actual concentration and the molar solubility, the concentration of magnesium and the molar solubility are actually the same number there. So this is the number I want to focus on. So at 18 degrees, it was 1.21 times 10 to the minus 3. Now at 27 degrees, look at that. Did the solubility go up or go down? All right, so this at 27 degrees, the molar solubility went down. So let's think about our reaction now. Where is the heat? If we increase heat and we get more solid because it's less soluble, it's now less soluble, which means we have more of the solid. Where is the heat located? Is it a reactant or is it a product? It's a product. Heat's over here. That's right. So it shifts that way when you add in heat. So obviously this one is exothermic. And I would say it's exothermic because the solubility of the salt, decreased as you raise the temperature, meaning that heat must be, being released. So if you increase heat, it's going to shift left and make less of the, make some of the solid, or make some of the salt not dissolve. So that one, this one's like an intriguing conceptual one, definitely, and it includes Le Chatelier's principle in there. So focus on that. Okay, so far I've covered two of the three kind of KSP problems. The other one is, of course, just directly having you calculate molar solubility from a KSP. So like this one, number 2, this is exactly, what is the molar solubility of strontium? Well, this is a 1-to-1, so they told me the KSP here, 7.6 times 10 to the minus 7, that's going to be, what, x squared? Because KSP equals x squared for the 1-to-1. Now for this one, molar solubility of strontium fluoride, in this case, this one is going to be, is that a 9? I can't see it, so I don't know why my pen won't erase either, but here we go. We're just going to do that and get rid of that as well. All right, so here, this one is 7.9 times 10 to the minus 10. And this is going to be the 4x to the third one. Exactly right. So this is like the third type of KSP problem you might see, where you're just doing regular molar solubility from the KSPs. Now, the interesting part here, though, is they're not going to ask you C. C is like that selective precipitation stuff, which we don't really do. However, what they could ask you, a simple question, let me calculate the molar solubility of each first, because then I have to show you. 7 square root. All right, so the molar solubility of strontium sulfate here is 8.7 times 10 to the minus 4 molar. Okay, so that's the molar solubility for this guy. Now let's look at this one. We would do 7.9 times 10 to the minus 10 divided by 4. And then we have to do the, that's not it. Clear. Then we have to do math and then the cube root. And this one is getting 5.8 times 10 to the minus 4 molar. All right, so they could set up a scenario here where they could say that you have like a solution that has strontium in there. No, wait, what's the common ion? It's strontium, right? So they have a solution hanging out here with sulfates and the fluorides in there, right? And they're going to slowly add, say, strontium nitrate to it. Like so. They're going to slowly add that to it. Now, which one should precipitate out first? Which salt is going to precipitate first? Oh, that's terrible. Which salt precipitates first based off of this information you've been provided? The molar solubilities of each, the KSPs of each. Which one's gonna precipitate out first? Is it gonna be the strontium sulfate or the strontium fluoride? Because you notice, once again, this one is 1 to 1, this one is 1 to 2. So should we directly compare the KSPs? When they're not the same one, we shouldn't directly. So we don't want to look at these. We don't want to care about the KSPs. What should we compare now? What are the values we need to compare to tell? Remember, this is X. What's X again? This is X for this one. Yes, it's the molarity, but technically this is also the molar solubility of each one. The molar solubility of the strontium sulfate is 8.7 times 10 to the minus 4. The molar solubility of the strontium fluoride is 5.8 times 10 to the minus 4. We can now, because we calculated the molar solubility, we can directly compare those. Which one is more soluble? Which one has the higher concentration? Yes, so this one is more soluble and has that will have the higher concentration of dissolved ions. So which one would precipitate first then if we just started adding strontium to a solution that has fluoride floating around and sulfate floating around? Which one's going to precipitate first? The one that has a lower molar solubility. Yes. The one that's going to precipitate first here is going to be the strontium fluoride. This one, if you slowly added strontium to a solution of sulfate, equal molar sulfate and fluoride, the strontium fluoride will precipitate first. That's because its molar solubility, the ability to dissolve, is less. So you would start seeing strontium fluoride come out of solution to a certain point, and then eventually the strontium sulfate would start also precipitating at a later time. You can actually calculate those values if you do the selective precipitation, but like I said, that's not on the AP exam, so we're not going to calculate those values. You just have to be able to conceptually compare the molar solubilities when the ratios are not the same. The one that's less soluble or has less molarity, means less can dissolve, that one will be the one that precipitates first. Also to point out too, if you had two that you were comparing that had the same ratios. So say something like this, say we had like AgCl and we had, what's another one? Like CuOH, like that. Copper 1 hydroxide and silver chloride. They're both 1:1. If they're both 1:1, I can directly look at KSP. I can directly look at the KSPs, and the one that has the smaller KSP would precipitate first. So if the ratios are the same of the ions, you can look at the KSPs. If they're not the same, you need to do molar solubility. Compare molar solubility, so the one with the lower molar solubility is the one that would precipitate first. So these are the three types of KSP problems that you're guaranteed to see tomorrow. You're going to get one of the three. Yes, the one that has a smaller KSP is going to, if the ratios are the same, is the one that will precipitate first. Good. Exactly right. All right, so that's the basic scenarios for, and if they aren't, then you do the molar solubility calculations, figure out the molar solubilities of each salt, and then the one that's less molar solubility would be the one that precipitates first. Okay. So kind of ran through most of the KSP stuff. As you can see here, like grams in 50 milliliters. So you would use the KSP in this example to find your molar solubility, and then you would take your molar solubility, which would be in moles per liter, and then just convert it to grams per milliliter. That's just the extra step here for this part. And then here, once you figure out the grams that can be dissolved per milliliter here, then you could, figure out how much would be able to dissolve. This is common ion here because it's NABR. So this one you would do like a rice chart with the common ion. Figure out the, how much would go in there. Okay. This one right here is molar solubility again. Molar concentration of I. Remember, the molar concentration of I will be double that of the lead, which is also equivalent to the molar solubility because this is 1:1. So iodide here would be double of lead because there's 2 of them for every 1 lead. And the lead is equivalent to the molar solubility because it's 1:1 with the salt in terms of the mole relationship. Yes, that is exactly right. That would be fine. All right, so here it says a saturated solution. Let's see here. The value of the KSP of the barium chromate is when the sample is added to the. What did they want us to do with that? I don't know what they wanted us to do with that. Oh, I think this is not supposed to, or this is, okay, assuming the volumes calculate their molar concentrations. Okay, whatever, that's fine. There you go. All right, so those are the basic 3 KSP problems that you will see. Now let's switch over to equilibrium. And let's take a look. Okay, so Le Chateliers. You're going to get like 2 or 3 Le Chatelier explanation type questions. What are some things that are definite, like it's going to trick you if you're not paying attention for Le Chatelier principle. What are the ones that don't ever affect the equilibrium shift? Let's list those out. Now, pressure can affect the equilibrium shift. So can temperature. But which one never? Yes, solids and liquids. You add or remove solids and liquids. Okay, these all should be no shift, put it this way. We're making a list of the no shifts. Adding, remove solids or liquids because they're not supposed to affect the equilibrium position. Right? What else? What else is on the adding a noble gas? Thank you. I like that one. Adding the noble gases like neon, argon, inert gases. That's a no shift. Oops. What else is a no shift? There's another one that I can think of. Catalyst. Yes. Adding a catalyst. That's a no shift. Good, right? Yeah, helium's a noble gas too. Yeah, any of those inert gases, right? Good. All right. So these are all no shifts. These are all the ones they try to trick you with, right? Now, it says right here, like if we're looking at this one, these are all gases, so we don't have to worry about that part of the equation. However, delta H is negative, so you need to know that heat is on the product side. Make sure you put that in there as well. So decrease the volume. Yes, it's exo. Delta H is negative, so that's telling us exo heat is a product. Decreasing the volume of the system. When you decrease the volume, what are you actually doing? Increasing pressure, good. So in that case, if you increase pressure, it goes to the side with fewer gas moles. All right, so in that case, this is 3, this is 2, so it would shift to the right towards the product. Adding oxygen, so we're adding in a reactant. Now, when this actual answer key was put out, they didn't care so much about this, but I do want you to make sure you write this in there. Adding in oxygen, which way does it shift when you add oxygen? Adding in a reactant makes it shift towards the products, right? So we're going right towards the products, but they also want you to note the KQ relationship here. So K must be less than, no. K must be what? Greater than Q here. When you add in, so remember it's P over R, right? So if you're adding in reactant, you're making your Q value less than K. And we know if you put K first and then Q, it points the direction of the shift. So when you would explain this one, adding in oxygen, what is it? Here it wants you to predict the effect of each of the following changes on the equilibrium constant and on the number of moles of SO3. So for this one, I would say the moles of SO3 is going to increase because it's going to, adding in the reactant makes it shift right towards the product, creating K being greater than Q situation, where you have, you have too many reactants, so it's going to proceed towards the products in order to get back to equilibrium. Now it says for equilibrium constant, does A or B actually affect the equilibrium constant at all? What's the only thing that affects the equilibrium constant? Temperature. So this would be none on K. This would be nothing on K. K remains the same. Only thing that changes K is temperature. That kind of declaration right there. So this one, we are raising the temperature. Now, we're raising the temperature, and we know the temperature, or that heat is a product. So we're actually increasing the products. Which way does it proceed in that case? Yes, it's going to go left towards the reactants. So the SO3 moles would actually decrease. Yes, less of that. And what's going to happen to K now? What happens to our K? If we're shifting left, we're increasing this part, decreasing, that part's going down. So decreasing the products, increasing the reactants, K is actually going to get lower. Yes. So the new K is going to be lower than the original one before you raised the temperature. And you can even use this in your explanation, that it's a ratio of the products over the reactants. So when you shift left, you are increasing the bottom number and decreasing the top number, and therefore the K ratio is less. You can use that in your explanation. Make sense? All right, so here, watch this one because it's a solid. You wouldn't want to include that. Okay, partial pressure of ammonia increase, decrease, or remain the same. So if you add in this, this is a no change, right? Temperature, once again, this time, the heat is over here on the reactant side because it's exothermic. Volume is increased, so that means pressure decreases kind of thing. So this side you would go to the one with more gas moles. And then adding in the two gases. If you add in this, it's going to shift that way. If you add in this, it's going to shift that way. All right, don't forget to explain though, as you know, here, once again, products over reactants. If you're adding in the products here, okay, making this number larger, that means that Q is greater than K, so it's going to shift this way. Don't forget to cite this part. They really want you to talk about the K versus Q. So when you ultimately, when you add in products, this now becomes Q, which is a bigger number than the original K. So that's Le Chatelier's, and you're going to get like 2 to 3 Le Chatelier explanations that are random and different from others. Okay. Now for actual, oh, this is a good one. This is a total pressure one, right? The total pressure ones. So this is the total pressure one is where you use Dalton's law of partial pressure. Okay. Don't forget for these kind that you need to set up your, rice table for this, but let's start with A because I'm getting ahead of myself with trying to look at B here, but I saw the total pressure part. Sulfur chloride is highly reactive, heated, it decomposes, blah, blah, blah. Okay, this is exothermic. That's probably important later. You might want to underline as you go. Well, you can't because it's on the computer, but like pay attention to that as you're going. Sample of 3.5 grams is placed in evacuated 1 liter. The temperature is raised. What would the pressure in atmospheres in the bulb if no dissociation of this occurred? So basically, it's asking for the partial pressure of this initially because nothing has occurred yet. So it's asking for the initial one. In this particular case, what do we need to do? And this is also one where we are incorporating more gas laws. This part, you need the ideal gas law. They gave us the grams, so we have to change that to moles first. So what? Sulfur is 32.06 plus oxygen, which is 32 there, and then the 35.45 times 2. All right, so this is 134.96, 1 mole. So I need the moles here for the end part. So that was an extra added conversion step that makes it a little bit longer. So N equals 0.02600 or whatever. Okay, 4 sig figs. It wants 4 sig figs. It tells you everything else about this. So we don't know the pressure. We know the volume is liter, 1 liter. We know the moles now because I just figured them out. We know the R value, and we want it in ATM, in atmosphere, so this is the 0.08206 number. And then we know the temperature is 375 K. This is going to end up giving me the partial pressure of our sulfuryl chloride, which I need this initial amount in order to do the next part of the problem. So you have to use, in some situations when it's asking for a partial pressure, pay attention to the fact that they give you the temperature, they give you the liters, they give you some way to find the moles. You either use the molarity equation, or here you're changing grams to moles. They're giving you the pieces of information that you need to put into the ideal gas law, or PIV-NERT. So let's calculate this. We get 0.026 times 0.08206 times the, what is it, the 375. All right, so this is giving me 0.800 for my atmospheres. That's a terrible 8, but that's basically what we got there. So this is my initial partial pressure. So when the system has come to equilibrium, the total pressure in the bulb is found to be this. Calculate the partial pressures of this, this, and this at equilibrium. Wow, this is going to be fun. So we get the Rice table. We got to do Rice. Rice. All right, Rice is nice. So we have SO2Cl2, SO2, and then Cl2. Now, initially, I have 0.800 ATM. I don't have these, right? So this is going to be minus X. This is going to be plus X. And this is going to be plus X. So 0.800 minus X plus X plus X. This is going to be all equal to the total pressure, right? Because all of them at equilibrium should add up to the total pressure. So when it came to equilibrium, it's going to equal 1.4 atmospheres like this. This is what I call a total pressure problem, where they make you use Dalton's law of partial pressure, and probably in a previous step, they're going to make you use PIV-NERT. So these cancel basically 1.43 minus 0.8. So X equals 0.63 ATMs. Now you can figure out these guys are both 6.3 ATMs at equilibrium, and then this one 0.8 minus 0.63. This is 0.17 ATM at equilibrium. So you'll see, you'll have a possibility of getting a total pressure one. This is the total pressure type problem. That's one possibility. Give your equilibrium expression, calculate the equilibrium constant. And here, because you have everything in pressure, I would go for Kp. That's what I would do. Now, if temperature were raised to 500 K, would this have an effect on the? Yes, it would. And it told us up here, remember, that it was endothermic. So you know which, if you were to raise the temperature, then it would shift right towards the products. And then you would have the products higher than the reactants, so K would increase. So that's how they ask that another time in here. Once again, they give you grams in this example, and they gave you 15 liters. So you have to calculate the molarity separate before you can even begin. All right, so that's part A, is calculating the molarity separate of the initial molarity of the antimony pentachloride. What is the pressure in atmospheres before decomposition occurs? Once again, they gave you the liters, they gave you the temperature. You'd have to change this one to Kelvin first though, and you would figure out the moles for this part, find the moles per liter. You would figure out the moles here. You would convert that to moles first. So here, this is just another PIV-NERT example where they're incorporating it. You're finding the partial pressure of this to begin with, like we just did. So that's showing up again. Oh, here's the percent. If this question was in that review, the review set of problems, if a certain percent decomposes, you know, if this percent is decomposed, you can calculate the equilibrium constant, either one. In this case, once again, you could choose, I think you can choose either one, because you could do the, starting with the moles per liter, which is A here, or you could start with the atmospheres here. So you could do KP or KC depending on which one you chose, because you know that 29% is going to decompose. So you would take 29% of your original value, and that would be the change amount. That would be the X value that's either being being subtracted from the reactants and being added to the products. So that's an easy one right here. Percent, you might see one like that where they tell you a certain amount of percent changes over. Well, that's how you find the X value or the change value. 1 mole placed in 2 liter, at a temperature different there. Is this temperature equal? Kc equals how many moles must be added to reduce the number of moles to 7.0. I don't know about that one, but I'm sure that's another rice table type problem because you have a new K value type deal. So the percent one, that's a good one. And on here, the ones where you're using the ideal gas law and the total pressure, that's another good one. Let's see here. Because I'm kind of seeing the repeats of what I just talked about. Here's another percent one of the original number. This one's also showing you when equilibrium starts to establish, because at 8, it's 8.37. At 10, it's 8.37. So it's showing you the total pressure of the system at that point. So you can assume that's the equilibrium total pressure. And that's where this would end up being like another total pressure type problem. Calculate the number of moles initially placed in the container. Assume the volume, okay, and so yeah, you would be able to work backwards from the total pressure here, and partial pressure, value of the equilibrium constant. All right, calculate. All right. Let's see here. The number of moles. So they gave us the temperature, the reaction total pressure in the container was monitored and reached. There was still some remaining that were recorded on the table there. Calculate the number of moles initially placed in the container. So RICE, we have CS, 2 COs. This is 0. We don't know what this is. This doesn't matter because it's a solid. And it's telling me the total pressure is 8.37. No, none of the K's have units. So this would be plus 2x, plus 2x. This would be minus x. So something minus x. Initial moles. Oh, I want moles. What am I doing pressure for? What do I want? Why am I doing that? I don't know. Anyhow. Oh, okay. Well, part 3C, really? Oh, that's not 3. That's 5. Where's 3? Up here. Oh, there aren't any units. Ignore this. This old question. Don't worry about that. Don't worry about, you would never be asked for K units at this point. So don't worry about that. All right. Because I'm getting off pace here and I want to keep going. I'm going to go ahead and let's see here. We did all the KSP stuff. Hold on. I'm going to go here because I want to look at that one because for some reason I'm blinking. That was on number 6, right? Let's see here. Yeah, did the Dalton's law partial pressure one, that's fine. So don't worry about K units. I know it's in there. That's from an old FRQ. They don't no longer require and have you put units here for any of the K values. It doesn't matter if it's KSP, KP, KC, KA, any of them. All right, that's still that one. It depends. For the most part, if you start off with no product at all, it's going to be subtracting from the reactants and adding to the products. If you know you're starting, see like here, initially these are zeros right here on this. So if you're starting with no product, you know it has to shift right in order to get to equilibrium. But what happens, and this is the next type of problem, I was trying to find one, but before I got stuck on what they wanted for this other part here, this one. Here's the equilibrium expression, is the Q problems. If they give you initial concentrations of everything, you have to figure out which way it's going to shift. So that's important. You have to calculate that. Okay, so, oh, they wanted you to do at time 0, the only gas you had in the container. Ah, see, that's the trick there to that one. Got it. Okay. Well, that makes sense. See, even I get stuck from time to time. But, yeah, so here for this one, the reason why they gave you this data table here. So see, I'm trying to work this out. The reason why they gave this data table to you is they're saying that solid carbon and carbon dioxide were placed in there. So at time 0, you're supposed to look here and know that that is your initial pressure of the CO2, because the only thing that's exerting gas in there is the CO2. The carbon is a solid, so it's not exerting pressure. So then you use the PV equals nRT, because now you have the pressure, you have the volume, which is 2 liters, and then you're looking for the moles N, and then you know R is 0.08206 here, and then the temperature is this 1,000. Wow, that's pretty high temperature. But now you can calculate N. So yeah, I knew there was a trick to this one. You need to realize at time 0, this is your total pressure, and you only have one gas in there at the beginning because the other one is a solid. But I want to get, yes, so you can definitely look over some of these. A lot of ones involving the gas laws with the KP stuff. But I did want to highlight and talk about the Q ones. That's finding Q. All right, so let me pull that up right now. I'm going to pull that up to go back. Actually, no, I have it on Classroom, so I don't need to, I can do it over here on Classroom, right? For that one, the Q problem, a good example of the Q problem would be in this set when we did these ones. Okay. So that's the very last problem on this one. And this would be another good one to go through for equilibrium problems, because like it starts off with some Le Chatelier review. Then it goes into like the regular basic problems. Okay, so that's all Le Chatelier's types of equilibrium problems, answers and explanations. So this one we did in class, but here are the answers. Being able to write out the expressions, that's fine, whatever. Brackets versus partial pressures, that's good. Now here, remember this one where you have to like flip and multiply, you have to remember to do the reciprocal, and then if it's multiplied by a factor, you raise it to the power of the factor. You're going to see maybe one of those type of questions on there, either by combining a series of 2 steps to make an overall, or just comparing it to an original K value where the other equation was flipped or multiplied. So that's always a good problem that can be asked in an FRQ. Problems with grams, once again, if you're given grams, you just change it to moles, you know, or you use the PivNert, you know, if you're finding a partial pressure that way that you need for your rice table. The other one, okay, so these are all PivNert type examples. Now we're getting to rice table ones, okay? So you could be given, the first type of rice table one you can get here is one like this where it gives you calculate the equilibrium constant when 3 molar reacts with this, and then it tells you what one of the equilibrium concentrations in. So review this type of problem because you can use the difference between the initial and the equilibrium concentration one to find your X value. Remember, if you're not given anything for the products, you assume they start at 0, so you know which way it shifts in that particular case. So here we're assuming this one starts at 0, and then you can use the 0 to 2.5 and figure out what X is. That's one type of problem. The percent one I told you about too, that one, you can also figure out the X value if they give you a percent. So that's one type. They could also give you one here. You could figure out the ATMs the same way. There's also, remember, this type where they give you the K value. They give you moles and then give you a different liter, so you have to recalculate the molarity. That's another particular one. But in this case, you'd have the K value, but you have a bunch of X's. So when you have that situation, you need to do the graphing and find the intersection so you don't have to do the quadratic. So don't forget, do the graphing and do the intersection. Find the one that gives you no negative concentrations, right? And that will allow you to get your equilibrium concentrations. So they can ask you to calculate K if they give you initial and at least one equilibrium concentration. Same thing for, they could ask you to calculate Kp that way, where they give you the partial pressures initially and then one partial pressure at equilibrium, or the total pressure at equilibrium where you can find X. You can still calculate Kp that way. Then the Q calculation. This is the one that was in the comment or in the chat. If they give you initial concentrations for all of them, or initial pressures for all of them, you have to do a Q calculation, which is basically just plugging in the initial ones into K expression, and you're really calculating Q. Then you compare the K to the Q to decide which way it's going to proceed to get to equilibrium. And in this particular case, we know K is 7.66. So when we do the Q calculation, Q ends up being 50. So Q is greater than K. So that means the reaction proceeds towards the reactants to get to equilibrium. So now you're going to subtract from the product and add to the reactants in that particular case. And also, we have the K value, but we do not have any of the equilibrium concentration. So this example problem also is one where you need to graph it and find the intersection. When you find the intersection, that's your X value. And that's the one that you plug in here to get your equilibrium concentrations, like so. So basically, when you're looking at equilibrium, going over the graphing, yes, so basically here, let me take this one into account. What's the K value? 7.66, right? 7.66, all right. Hold on, I'm gonna try to do this to make it more efficient. Let's go back over graphing just to make sure everybody can do this. Okay, so these are the equilibrium ones, and we know that the K value is 7.66 for this problem. So here we go. We're gonna put it here. I'll go away. All right. Well, here, it's just going to make me do it at the top. Oh, no. All right, never mind. Let's put in, oops, that's not it. Home, insert, page break. There we go. Now I can put it up here. Oh, no. Why did you do that? Oh, you did that because I have to now format you. There we go. All right, so here, you know, the K was what, 7.66. Hold on, I do need to look at one more thing here. What was our reaction? Oh, it's this one. Okay. So this is 3H2, this is N2, and this is 2NH3. All right, so that means our expression, the K expression, is going to be 2 of the ammonia squared, or the ammonia squared over the hydrogen to the 3 and the nitrogen, like so. So we plug these in to our calculator. So we do 7.66 equals the 5 minus 2x squared on the top over 1.0 times, or plus 3x cubed, and 0.5 plus x on the bottom, like so. So what you do is, in your calculator, you put this in for y1. You know, there's that y equals button at the top. You put this in for y2, and then if you do alpha, and then y equals, it gives you the ability to do numerator over denominator for y2. And then it's easier to put this in there. But basically you type this in, y1, y2, and then you hit graph. And when you graph it, it takes a moment to like put the two graphs up there, right? Follow me so far? Then in order to find the intersection, you do second, and then trace. You do second and then trace, and that is the going to get you to calc. And let me look at that. What does that say? Second, trace. Then it gives you a list for calculate, and you want to do the number, it's number 5 on mine, but you want to do the one that says intersect. Okay, I do intersect, and then it'll say first curve, and then it says second curve. You just hit enter, do first curve, enter, second curve, enter, and then guess, and then enter, and then it should say, hold on, I'm going to look at my calculator now because I did just graph one. In the lower corner, it should say like x equals and then a number, whatever that number is. And that is going to be your x value. So first curve, enter, second curve, enter, guess, and then it gives you the intersection. And you want to make sure, my son did point this out to me because I was trying to graph something the other night and it wasn't working. You want to make sure that your minimum and maximum values are set within your window. Does everybody know how to get to the window and fix your min and max numbers on your calculator? Because there's like x min, x max. You want to make sure these are within your like intersection value line, so that you get the right one. You get the right intersection. So that's kind of the gist of like the graphing way. I mean, you can always do all the multiplication and stuff and do the quadratic, but who wants to do that? All right, so back to the, what if they don't give you the K value? What are we talking about there for that one? Or is that something else? Is that no, they have to give you the K value for this problem because they don't give you any of the equilibrium concentrations. So those are the kind of scenarios. They either give you, two initials and an equilibrium and you can find K. Or they give you initials and K and you can find equilibrium ones by graphing. Or they could give you initials and then a percent that decomposes, or percent that changes over. And then if they give you the percent, remember, you can always find X because you know how much the change is going to be. The only time you're going to have to determine which way it's going to shift is if they give you initials for all of the reactants and products. If they don't give you initial concentrations or initial partial pressures for everything, one of them is going to be 0, and it's always going to go the direction, it's going to proceed towards the one that didn't start out with anything. So the only time you have to worry about Q is if they give you a initial value for every single reactant and product. If say there's 4, there's 2 reactants, 2 products, but they only give you 3 of the 4. Well, the one that they didn't give you, that's the direction it's going to go, towards that one. Or say there's 1 reactant and 2 products, and they only give you the initial of the reactant. Well, you know it's going to go towards the products. Or say there's 2 reactants and 1 product, and they give you the initials of the reactants but nothing of the product, then you know it's going to shift towards the product. This PowerPoint is worth going through again and looking over, this one about the reviewing equilibrium problems. The KSP free response problems, those ones I just worked, those are worth reviewing as well, going through the answer key very carefully with a fine-tooth comb. And then, looking at the equilibrium ones too and going through that PowerPoint where they're all worked out for you. Don't worry about, units for K. We never ask for units for K. One other thing I did want to point out to you that's kind of a trick. All right, so here's the checklist. We pretty much went through Le Chatelier, so that's 16, 17. 18 is Le Chatelier, 19 is Le Chatelier. Like I said, don't worry too much about 20 because we are going to go back over the adding OH when you have H or adding H when you have OH. We'll talk about that more in acids and bases. That kind of stuff. If you cause a precipitation of an aqueous solution, that's going to remove the ion from the solution. So therefore, it's like removing it, follow Le Chatelier's for that. So basically 16 through 21 is Le Chatelier's. Okay. Understand the equilibrium expressions. Remember that if you're writing out a partial pressure one, use partial pressure notation. If you're writing out one for concentration, use concentration. And let's see here. Oh, this is a very important point right here. Oops, didn't mean to do that. I was trying to highlight it. Anyways, this one right here. This is a very, very important thing to focus on. What does that say? If K is very, very large, the reaction essentially goes to completion at that temperature. So if they give you one and they say, like, looking at the extent of K there, and it's very, very large, how do you treat that particular problem? What is the important trick about that? The very, very important trick about that. When you have a very, very large K, it essentially goes to completion. So it's not an equilibrium system. So when you do the math like regular stoich. You don't set up a rice table. You don't do that. They're telling you K is super large. You just treat it like completion and just do regular stoichiometry. So sometimes that gets thrown in as a trick. I guess it could be for either. KEQ, like KEQ is just the equilibrium constant for like a regular equilibrium system. KSP is just the equilibrium constant for, for solution, dissolutions. Remember I showed you that chart on, on the complex ion formations. Those ones essentially go to completion pretty much for the most part. Let me show you that again. That's going to be in the KSP notes right here, right? Okay. So here, I can show you real quick again where it is, but at the end we talked about complex ion formation. And if you look at some of those K values for complex ion formations, they're so super large that they essentially go to completion. So like here, it's showing let's see here, this one, this CuCN4, the cyanide, the copper 2 cyanide here, 1 times 10 to the 25th. That's a, K is super big and it's going to go to completion and you treat it like regular stoichiometry. This iron one too, which is like 1 times 10 to the 35th. This is another one, 1 times 10 to the 42. Those Ks are so big, there's no real equilibrium position. They just go to completion. So they would want you, if you were given something like that in a K that's super big like that, you would just do regular stoichiometry with it. And just assume it goes to completion. Okay? All right, so I have run through pretty much everything that was in my head. But if you have any additional questions, be happy to answer some at this time. But I pretty much like highlighted like the main aspects of what you need to make sure, the type of problems you need to be able to do. Does anybody have any questions? All right.